And so we've stopped at Ptolemy and his model. We were with geocentrism, and we've seen that there was no killer argument to say it's heliocentrism. So people adopted geocentrism out of many philosophical arguments. Now we're going to make a leap in time and reach Nicolas Copernicus. Now, you might say, well, nothing happened in between? Yes, things happened in between. So Nicolas Copernicus, just to get the story, is the one we accredit with establishing heliocentricity for good. Now, it doesn't mean that at his time we did find the killer argument, the grail, if you'd like to think of it in this way. Well, Copernicus was some kind of clerical person. And what you need to know is that in the interval until Copernicus, many people worked on the solar system, trying to improve the accuracy of Ptolemy's model. Because what I didn't say is that Ptolemy's model did explain a number of things, but there were things that were left out. Not that heliocentrism a la Aristarchus, the example we've seen, solved them. It was not. So, for example, Islamic astronomers, Arab astronomers, worked a lot on the model to improve it. And in so making, they brought a lot of new mathematics, modified models, actually something they call non-Ptolemaic model. One of them is Ibn Shatir. Now, why do I mention him in particular? Well, he basically, if you look at it, he died about 100 years before Copernicus was born. And it seems today, with the discoveries of his work in the 50s of the last century, 1950s, we've discovered that some of the things that Copernicus used were actually also coming from Ibn Shatir. Now, some scholars think that Copernicus used them but didn't really understand that, the models. The main difference is that Ibn Shatir was still geocentric, so people were still trying to modify Ptolemy's model, keeping the Earth at the center, whereas Copernicus adopted a completely different stance. So what's the difference, basically, between before, the proposals before, and this time? Well, one thing that's key is the fact that Copernicus was able to measure the distance to planets in an easier way, the relative distance to planets in an easier way. That's an example with Venus. So you get what you call the upper conjunction. It's basically the largest distance between the Sun and Venus. And by using geometry, I mean, for those who know some mathematics, once you know the angle 46 and you assume that the distance to the Sun is 1, you're able to measure the distance to the other. That's simple trigonometry. There was also a way to measure the distances to Mars, Jupiter, and Saturn. And these were, quite interestingly, especially if you measure it many times and you calculate the average, these were quite close to our current values. Now you might say, how did we get our current values? Now we measure it in kilometers today. It's not just 1 AU. That's something we're going to talk about when we look at a parenthesis opened on measuring distances in the universe. Parallax is one such method. I went over parallax briefly before. So you get the distances to Mercury, Venus, Mars, Jupiter, etc. in an easier way and in a more apparently accurate way than, I mean, we didn't know if it was accurate. We didn't have a different way of actually measuring the distances. And two, it explained retrograde motion in a simpler way. Now, my drawing is a bit misleading because it gives the impression that Copernicus just took circles and got the motion of the planets on a circle. Actually, he didn't. Because again, that kind of motion alone, a circle, didn't explain completely all the observations you saw in the sky. Now, we didn't go into all the details, but these are some of the details. So you did explain retrograde motion in a simpler way. You don't need an epicycle, just have it projection relative to the skies. Now, why Copernicus is a major change? Because the first time, it's a complete model that's actually published with calculation devices, with everything, with a lot of mathematical details, inspired by previous astronomers like Ibn Shatir. So Copernicus actually worked for about 40 years working it out. But then the interesting thing is that at the time, the church used to say this book is allowed, this one is not. And heliocentrism was forbidden because we used to think that there were something in the scriptures in the Bible that we interpreted as, well, I mean, the sun moves around the earth, not the other way around. Again, don't forget that we don't have an argument for heliocentrism. So when he published his book, he was basically dying. And the story says that he got the book on his deathbed. Furthermore, his counselor actually wrote a preface to the book saying that this was just a model to ease up calculations, not necessarily something that was representing reality. Although we think that Copernicus thought that heliocentrism was truth. And so he avoided the index until 1616. So for almost 75 years, Copernicus' book was among the hands of everyone. Was read, was discussed. People, you had some, by the time Galileo was there, you had a faction of people who used to believe that this was reality, and a large fraction. And especially that it was timed also at the time of the rise of Protestantism with the Reformation, etc. So you've got people who started moving away from the influence of the Catholic Church and Rome and the Vatican. Now, what about predictions? Well, the problem is actually they had the same precision for prediction between Ptolemy and Copernicus. So again, why would you adopt Copernicanism? No reason. One is complex, one is simple. Okay, so what? No final argument. Now, it seems also that it was sometimes even less accurate than Ptolemy's model. And actually, Ptolemy's model was not accurate. There were a number of things that it couldn't reproduce. Actually, all the attempts used to be able to reproduce more things about the sky and predict more things about the sky, but not able to reproduce a lot of other things. So Ptolemy's model was not accurate fully, and Copernicus' model was not accurate, but it was simpler. And again, no killer argument, parallax. Now, interestingly enough, we didn't wait for parallax to kill geocentrism. Now, two other persons come into play. The left-hand side gentleman is Johannes Kepler. We've seen his laws before. And the right-hand gentleman is Tycho Brahe. Tycho Brahe was a nobleman. Kepler, no, was a common man. The difference between the two is that Kepler was a mathematician, and we're going to see what they did. So Tycho was a master observer. We think that, I mean, we have evidence that he was the best ever observer with the naked eye. We didn't have a telescope yet. Telescopes were invented slightly after the day Tycho Brahe died. So he developed very strong, very powerful instruments with the naked eye to measure as accurately as possible the stars. Now, the other thing is that he was an aristocrat, so he had access to a lot of money. And he owned an island in Denmark. At some point, he had problems with the king of Denmark and moved to Prague, where he found a king to actually support him again. Now, the interesting thing is that he was fond of astronomy, and he collected a huge amount of observations. Now, we're going to try to see why he did that. So, as I said, he achieved precisions never before achieved. And today, a review of his books is showing a tremendous achievement by that gentleman. Now, Kepler met him in 1601 in Prague. Now, Tycho had a problem. He didn't believe in Copernicus' model. But he was not really a Ptolemaic guy. He did develop his own hybrid model. Why? Well, because at some point, he measured the distance to a comet. Parallax. I'm going to say, wait a minute. What are we talking about parallax here? Not parallax of stars. Because you could have parallax from two sides of the earth. The same way that you have parallax from two sides of the sun. You could be in the morning on one side, in the evening on the other side. You look at the same object, you're going to measure parallax. So he could measure. He was able to measure something like that and discovered that the orbit of a comet is actually egg-shaped. Now you're going to say, okay, We just said ellipses. But then people at the time used to believe that all orbits were spherical, were circular, because it was perfection. And actually, people used to place the planets on large glass spheres. Glass because it was transparent. And suddenly you've got something that's actually going through the glass. So no glass. And suddenly you're beginning to change the philosophy of things. So he developed his own model. I'm going to say, wait a minute, what does that mean? The Earth is at the center. It's a cross. That's a symbol for Earth. And the sun is that star there. So basically we're saying the sun orbits around the Earth and everything else orbits around the sun. Now, you might think it's awkward. Yeah, but I mean, again, people were trying to make sense of the world. And so, to prove his model correct, there was something quite tempting. The planet that has a narrow on top, Mars, the symbol for male, actually gets quite close to the Earth. And it gets inside of the orbit of the sun around the Earth. So he thought that he could measure the distance to Mars by measuring parallax. So by looking at the position of the planets all night long when it's at closest approach, looking at it from the start of the night to the end of the night, so you've actually shifted your place on the Earth, you could measure the distance to Mars. And he wanted to prove himself correct, but he was not good in mathematics. كان كسلان بالمات إذا بدكم. ما كان كسلان بالمات. He was good, but he was not a brilliant mathematician to be able to get the complexities of models to explain this. So he brought Kepler in. Kepler was a poor guy who was a teacher in mathematics. He was searching for money, and Tycho heard about him. He brought it in. But he knew that Kepler was a Copernican. So Kepler was a believer in Copernic, من حزب كوبرنيك. هو من حزب غير شيء, Tycho. His own party. He was trying to create his own party. So at some point Tycho hesitated to give him his treasure trove, all his observation of Mars. At some point he ceded and gave him that. Now Kepler died, Tycho died a year or two after Kepler joined him. So Kepler inherited those books and started working on them, trying to fit the model. He first started with a circle and epicycles. So he was basically trying to get into the philosophy of the time, while still being Copernican. Don't forget that Copernicus' model had circles and epicycles. Same thing. He got somehow a model, but he still had a few points that didn't match it, working on the orbit of Mars. And then he started from scratch again, and suddenly it was all there. When he let go with the circle, when he let go with the epicycles, when he put an ellipse, it fitted data perfectly, and he found it. So that's where we got the Kepler's laws. The other interesting thing is that Kepler also worked on trying to get the reason behind the motion of the planets. Now, why was that? Because one argument basically was, how would the moon be able to catch up with the Earth? Because people, even in the Ptolemaic model, had an idea about distances, expectations. And they thought that if you place the sun at the center, the Earth would be moving too fast and the moon couldn't catch up with the speed of the Earth. So that's why you needed to put the Earth at the center. And he was trying to search for a reason. At some point, he imagined that there was some kind of hand extending from the sun that was pushing the planets around.